All right, we're going to be covering just principles of motors. So we'll start off with single phase, three phase. What's the difference? What's the primary things we're trying to pay attention to? We'll kind of roll from there. Single phase, three phase. What is the primary difference? Obviously, single phase is going to have, just an L1, L2, and that's it. So each of these will be their own phases. And this is where single phase can get a little there's a couple of directions it can go, and it all depends on the stator. Either way you go with it, it still requires a capacitor in order to facilitate a kind of the third phase, if you will. But you can still have the 120 volt single phase motor or a 240 volt single phase motor. End of the day, it's still single phase. You've got two legs of power, end of the day. Well, that second leg could be an actual power leg, or it could be just a neutral leg. Either way, you've got two power feeds coming in. That's the whole point behind the capacitor, without taking a nosedive into some crazy science behind it. It's the capacitor facilitates on a standard permanent split capacitor motor, PSC motors, which is the majority of single phase motors out there. It's simulating that additional energy that's needed in order to turn that motor efficient, which is where three phase doesn't need the capacitor. So a single phase motor is coming in, circle, winding, and then we have a winding over here, coming off, over this, and bam, okay? This is your start capacitor, or your capacitor. Single phase motor, right? A three phase motor has a couple of different configurations on the windings, and so whether that would be of L1, 2, 3. So you have what is known as a Y configuration, or you have a delta configuration. Okay? Those are your two three phase application motors. The vast majority of them that we use is going to be, they come as a delta configuration. And now, something I want to point out here, and I've recently gone down this road myself. By the way, this will be L1, 2, L3, L1, L2, and L3. From an electrician's standpoint or electrical standpoint, there's two types of power. What are those two types of power? Y and delta. From a motor's standpoint, there's two types of motors, commonly. We're not talking special case here. They're Y and delta as well. Two different conversations. I myself am guilty of making a mistake for a long time of looking at it from the same viewpoint, and it's actually come to find out wrong. So a majority of our buildings, actually all of our buildings, I don't know of a single building around our area that I've worked on personally that has a delta configuration on the incoming power to the building. Okay, it's going to have a transformer. It's going to basically look like this, right? So instead of a motor shape, just think of that as a transformer shape. So the transformer for the building is going to have, this is your delta sign, for the transformer. And you can actually walk up to the building transformer and look at it, and you'll see one of these two symbols on it. Now, like I said, every building we have that I'm aware of is going to have a Y configuration. But majority of the motors we use on the larger horsepower, say 40, 50, 60 plus horse, are going to be a delta configuration motor. And the difference is literally how they're wired. With a delta, you end up having these crossover legs, right? that come off. With many of our three-phase motors, you open the pecker head up, there's more than 3 wires in there. Most of the time there'll be at least 6, if not 9 at 7 times, right? I think vast majority of them are probably gonna have 9 wires. And that's literally right here in the middle of the winding where it splits off. And depending on the voltage you have, depends on, and well, that's where you get to high voltage or low voltage, will depend on how you configure these wires. So let's say this will be 1, 2, 3, and this may be 4, 5, 6, 7, 8, 9. And then on the pecker head, it'll tell you which configuration to use depending on the voltage you have, right? And that configures this winding to be able to operate within that parameter. This is your primary difference. You're talking very different winding configurations at this point. Most of the time, the only time we will see these is typically on compressors. So specifically, you start getting into like chiller size equipment or the Carlisle 06Ds specifically. So the 06Ds I think have a Y stator on them. And so, but some of the bigger ones like the 06E, if I remember right, I think the 06E has a delta. They use a delta configuration, it's a bigger body compressor. Anyway, you get into screws and you start getting into those much larger motors. That's about the only time we start seeing this Y configuration pop up. Vast majority of your blower motors, tower fan motors, all of those are going to be a delta configuration. So your common and your run are the two that receive the power. The start is only pulling through the capacitor. And that's why if you do exactly what you were talking about and you switch those, the motor will run backwards, which I'm sad to say I run into more frequently than I really care to. It's way too often that I see these 2 wires switch. So there's a couple of methods there's 2 primary methods of motor configurations. You have a 3-wire and a 4-wire. Okay? In discussing 3 and 4-wire, we are not talking about the speed tap. You can have, I don't care how many speed taps you got out here, right? It could be 3, 4, 5, 6, whatever they chose for that particular day. Now, honestly, they're usually just no more than 4. But point is, that's not what I'm referring to. What I'm referring to is how many power wires are running. Now you've only got 2 incoming wires for the actual power, but in a 3-wire scenario, what typically happens is this isn't going to come across. This will come down and go straight to the capacitor, and there'll be a separate wire tied to the capacitor coming back.
How is that any different though? You just drew it differently, but technically it's not.
Right.
The motor itself will have that wire.
So in this particular case, there are 3 wires for power coming out of this motor. Only 3. 1, 2, 3. A 4-wire configuration is going to look like this. This wire, so typically this will be, say, we'll call it brown, right? This will be just a straight brown wire. This one will be a brown white. And if you ohm this spade to this run wire terminal, right, it's going to show 0 ohms because it's shorted on purpose. It's the same wire, is what I'm saying. It didn't matter if you took this brown white and put it where this violet wire was. You could trade the wires, it would have no impact on how the motor ran. Because at the end of the day, they're the same wire.
Connected to the same spots on the motor.
Correct. And so many times, the manufacturers started doing this because people couldn't wire them correctly. Just flat out, right? They gave you 2 brown wires to plug into, just so you understand without a shadow of a doubt, despite your training or lack thereof, you knew that those 2 brown wires go to your capacitor. Period. And it's just straightforward. Nothing else goes to the capacitor other than those 2 wires. Because manufacturers get tired of having warranty failures on stuff that wasn't true warranty. So they figured, well, it's cheaper for us just to add a wire and make it simple for you than to keep paying this warranty for people's lack of training. And you can interchange them all you want. You can take a 3-wire out and put a 4-wire in. Most of the universal motors that you buy at the supply house that, you know, we keep trucks, or we don't, but many companies keep on their truck stock, are 4-wire motors. So it doesn't matter. What matters is you'll need a jumper versus not, right? So in a 3-wire configuration, and you'll see this in condenser fan motors too, right? This is the same exact principle. There'll be a jumper from the contactor to the capacitor, and then the run wire will plug in at the capacitor versus the contactor. It doesn't matter which side of that wire the run wire lands, whether at the contactor or whether at the capacitor, as long as it's on the run side, the L2 side of the circuit. And so, but that jumper wire freaks some people out just because it's an extra wire they don't understand what to do with. That's why 4 wires for many people just become preferred, because it's less that they have to understand. Let's talk about applications. Air handlers. We got a wide variety of different air handler motors, right? Let's start with just single phase in general. That motor is controlling the lifeblood of everything that we do, right? That blower motor is probably the most important part of that entire system, because end of the day, you know, when you get down to the brass nuts of what we're doing, is we are controlling air and the conditions of air. And there's only one device in the entire system that has anything to do with the physical air. It's the blower motor. And so without the blower motor, you've got nothing. You can freeze a coil up all day long, right? It doesn't do anything to condition the space. Everything in that system revolves around that blower. So it's important that we make really wise decisions on things like the right fan speed, the right filters, whole 9 yards. One of the things I'm going to bring up now versus later is shaft grounding. Okay? It is extremely critical that any motor that exists on a VFD has some form of shaft grounding, whether external, which majority of the time, if it's an external shaft ground, it's going to be aftermarket, or they'll have a tag on the pecker head that is saying it has an internal ground on the shaft.
Is that just in like words or like a symbol?
No, it'll be words. It'll be physically stated usually with a tag. Hopefully the tag doesn't wear off. Majority of your older motors are not going to have any form of shaft grounding. And like I said, if it has a VFD on it, that's a problem. So is anybody familiar at all with the shaft grounding theory? Let's start with the basics, okay? We have a sine wave right there, right? That's a pure, true sine wave. All right, this is what's coming through your starter. What is this?
That's a monoclave.
That is a VFD sine wave.
It's a sine wave. It's a PWM, a pulse width modulated sine. Okay? Totally different concept. And yes, this is coming out of a VFD. It goes into the VFD looking like this, right? On an oscilloscope. Comes out of the VFD looking like this. Stretching my own understanding of the whole process and principle is this sine wave, because it is artificial in its creation, right? This is actually DC voltage being simulated into an AC sine wave via positive and negative pulses on gate modules, which we call inverters, right? It's built into the VFD. This does not create a true pure harmonic wave internally in the stator, and you can hear it. Like once you get familiar with it, you can hear the difference in the motor running between a VFD driven motor and a straight, just hard starter motor. There's a literal sound difference, and you can hear the pitch of the harmonics off of this pulse width modulated wave. So if you can physically hear it, we've advanced enough in the industry now to understand that what does that do to the actual motor itself? Well, we've realized that we've created a massive problem for ourselves we didn't realize we were getting into. So VFDs are great, but we have found a major drawback. So in the process of the stator, right? So we have the stator here. Inside of there is your rotor. Okay? Going through the stator, coming out. And you've got your shaft. While this is rotating, and the magnetic fields that are being produced to modulate the speed, the pulse width wave is actually inducing through the harmonics of it. It's producing a physical charge inside of that rotor, to where that rotor is actually becoming electrified. Problem with that is the rotor doesn't have any other ground source vast majority of the time, because how are we connecting motors to the load, right? What is the load? The fan, right? So how do we connect the motor to the load?
Fan,
Belt, or if it's pump,
shaft or
coupling, right?
Isolated.
If this, I'm not even going to go there. I was going to say, if this was a direct drive, you have less of an issue, but actually you don't, because even if it doesn't discharge through the motor bearings, it'll still discharge through the blower bearings. So even a direct drive doesn't solve your issue. You still have the same problem. So what happens is, because this is usually isolated, right? So there's a rubber coupling on a pump that separates the motor shaft from the pump shaft. On a majority of our air handlers, we've got belts on the system. Well, obviously the belt it's an insulator. It's not conducting anything across it. There's only one place for that charge to go, and it's right through the bearing. And then depending on the severity of it, over time, those bearings will pit and tear up. And motors that used to last 10, 20 years, you can't even make them go 5 anymore. If you get a year out of them, depending on the motor and the setup and just how harsh of a load and how dirty of power you give that drive. As part of our issue too that we have in our area is we have extremely dirty power that it's horrible. Before ERCOT, and the whole freeze and all that stuff, before any of that even happened, we already had major grid issues in the Travis County, Central Texas area. East Texas, where I'm originally from, even has major power issues, not to the same extent as Central Texas, but they do exist. We've had this for a long time. It has only gotten worse. Many of our VFDs that fail out in the field fail because the drives just couldn't get clean enough power. And it just, over time, it just getting pounded and pounded and pounded. Those have SCR in them, silicone controlled rectifiers that convert that AC to a DC, right? That dirty power wears those out. And VFDs really perform their best when they have that clean, they know what to expect. It's consistent. You take that and add that to this as a general problem anyway, and we have motors that won't even last a year before we're having bad bearing readings through vibration. So to resolve that, we literally, we put it's a floating ground point. Okay, so the aftermarkets that you can have installed, that we take them to Hamilton or somewhere, have them put in or done, take it to any motor shop. They'll have a floating point touching the shaft, usually external to the motor, and it's just, that's all it's doing. Its sole job is to give an alternative source for discharging the rotor other than the bearing. Most of your factory done motors that come factory shaft grounded will have they'll have a brush kit or something installed internally most of the time. That's the ones I see, and they'll usually actually say that, has a brush ground kit or something along those lines.
How does that floating point look? Like, is it just like a little metal thing tapped in the side of the shaft, or how does it actually physically look?
Yeah, so it's you'll see a steel ring that'll be screwed. They've tapped some holes and it's screwed over the shaft, centered. And most of the time, I think they're usually like a brass type material. They're usually a softer material than steel, so they don't wear into the shaft. And I think they're usually a brass or bronze, something of that nature. And that's all it is. It'll have a slight curve to it naturally from the factory. That way it marries to the shaft better.
Okay.
Yeah. And so all that, it comes prefab that way. And then it's got a push spring behind it. And all it needs to do is just make one point of contact. That's all it's got to do. Now, one of the things to keep in mind is that the spring and those ground rings do wear out. They can get to where the spring or the ground pin will begin to stick, and it won't properly apply pressure against the shaft the way it needs to in order to just do its job. So those are our little things we have to pay attention to, because if we don't catch those things, we're going to fail a motor. And many of the manufacturers now realize this. Baldor in the last couple of years has now started releasing articles about this exact thing, because it became a big enough issue that people just didn't understand why we kept having failures. This was across the board industry thing. Honestly, this is something relatively new to the industry as a whole. Most people that I meet don't have any idea. And there is a technical term that I don't know off the top of my head for this whole phenomenon. They actually have a scientific word for it, right? Like psychrometric. This is a recent discovery, and I say recent within the last few years. And the manufacturers are now trying to push this information out to their contractors, as best that they can.
So they can save all their motors.
Well, that's exactly what it is. Yeah, they're tired of warranty.
Because you get a bad name, all your motors go.
No, and that's exactly what happened. I think Baldor probably has taken one of the worst hits, at least in our area. They're one of the more common ones, and they did have a reputation starting to form about them. Oh, just constant bearing issues, bearings.
So what stopped it, electricity being as it is, from grounding still into the bearings?
So we want to give it a path of least resistance.
Yeah, I see what's something more conductive.
Well, I mean, we got a direct metal contact all the way through the bearing. There's just the same path of least resistance.
Inevitably, though, what we're accomplishing is the bearings, because they roll and there's grease, don't always make perfect contact. So a literal charge is able to build and then discharge. With shaft grounding, the charge is never even there. So whatever electrons would be generated or induced, they're always getting passed on back to ground. This is extremely important. And this is a difficult conversation we're having to have with a lot of customers. And we have documentations, we have articles. How well we make things comfortable is based on how well we move the air, more than just condition it, right? We have to move the air properly, which is why the air handler is such a critical piece to the entire machine, because we have more than just sensible load. What is that? So we have sensible and latent loads. We have to be mindful of that. And it's very easy to process the sensible load. And most people, we go into buildings all the time, they're running 1.5 inch, 1.75 inch statics. And I asked them, I had one about a month ago, had a 1.8 or 1.7 inch of static he was running. Why? Well, the end result was, oh, that's just how it was when I got here. Just never did nothing about it. Nobody's ever said anything. Well, what you're doing at that point is you are just putting so much additional wear and tear on that motor, right? So this has a direct correlation to the motor, because this is where we start getting into centrifugal theory and lift. Okay, I'm not going to try to go too deep into the science of this, but I want to give some understanding. The whole point of this class is I want to give you some understanding of the motor and how we can properly take care of, utilize, and protect these motors from abuse and just efficiency standpoint. Lift is literally we can calculate compressor lift and refrigerant system. It's your discharge pressure. So this discharge minus suction, which in our air handler's case would be supply minus return. Okay? This is where your lift for an air handler, your blower motor, comes from. It's a centrifugal force device. With that, the higher this is, the more work you're having to do. And you can get into what is known as a stall, right? So stall is where you literally get so high on this differential that the blowers just physically can't do it.
You're just pushing back on it?
Yeah, there's so much back pressure coming back, and there's so much negative behind it. You literally get to a point where the motor just kind of falls into a stale state, where it's just not actually moving the amount of air. The air literally gets just trapped in the louvers. Now, if you start getting into, well, I'm not even going to go there. It gets trapped in the louvers. That is where you get into a true stall for a centrifugal blower. We have to avoid that. What is the base design principle for a standard VAV box? Because the whole point of this air handler, on the majority of our applications, especially commercially, is to control what? Maintain static for VAVs. We just need the VAVs and the ductwork to have the proper amount of air volume going to them. What is that design? What is the standard design pressure on any system? Like when the manufacturer sits down and I'm going to build this VAV box, what pressure are they expecting? 1 inch. 1 inch. That's all it is. The only reason, in my opinion, to go more than 1 inch on any duct system is either leaks or poor design. I will vouch. There are systems out there that are very poorly designed, and the only way that those engineers can get the proper amount of air to the furthest boxes, which are your main problems, is by ramping that static up to 1.25 inches, 1.5 inches. They don't have another choice. So those scenarios do exist. They're not ignorant. They just don't, it's what they're dealt with. But the vast majority of the systems out there, that is not going to be a requirement. Anything above this 1 inch mark, you're not doing anything for the VAV, because it's set to control a set amount of CFM regardless. You trying to force more air to it.
So the VAV goes off differential pressure, right? So how does a higher static produced by the air handler affect how it opens and closes?
Because at that point, the higher static means it has to close more, which means you're trying to run a higher static, you end up just deadheading the system that much more. Let's just say a VAV receiving 1 inch of static is able to maintain the damper at 50%, at 200 CFM, okay? It's being told by the automation, you need to do 200 CFM to satisfy this room, period. It doesn't care what it has to do, it's going to achieve 200 CFM regardless. Well, you bump this up to 1.5 inches, well now it has to clamp down to 25% to still maintain 200 CFM. The CFM doesn't change. Our damper position does, and the only thing we accomplished is put more work on that motor. The VAV is calculating total pressure minus static pressure gives you velocity pressure. Velocity pressure is not actually measurable. We can't physically measure that, but we can calculate it based off of these two, because total pressure is static and velocity combined.
Total's the one facing the stream and static's the one facing away.
Correct. So it's taking those two static readings, subtracts them, velocity pressure, then it looks at the duct diameter on the incoming side, which if it's 6 inch, so if it has a 0.2 VP on a 6 inch, duct.
Static goes up as your static pressure, because that's part of your calculation of velocity pressure, correct?
Yes.
As static pressure goes up, goes up, how does that affect velocity pressure? Well, I guess if you just look at it, you need to know what total pressure was in whatever given system.
Yes.
And as static pressure goes up, then the velocity pressure, it will do what? Because it'll go up as well because you're just subtracting.
Correct. They'll correlate together.
Right.
So because the static is higher, the velocity increases with it.
Right.
And it's a like-for-like relationship. Because again, that box, what it's trying to do is it just wants to maintain a 0.2. Like, that's all it sees. The box, the logic just sees, okay, I want a 0.2. Now, the graphics interpret the rest, and it spits out CFM and 50% and all this other stuff for us, because that's what we understand. But as the controller inside of that VAV, it just sees I have a 0.2 VP, and I know that I'm programmed to have a 6 inch inlet duct. I know that that's exactly what I'm being asked to do right now. By increasing this pressure, the only thing you do is you lose efficiency on the motor and the whole system. And you put extra wear and tear on the drive components, on the motor itself, on the blower, the bearings. It's just a domino negative. So we have to be careful not to fall into that trap. Again, our goal, our job is we're trying to protect that blower. That motor will live and die based off of these numbers. It's hard to have that conversation with the customer, but if they want 20 years out of that motor, this is how their system should be set up. If it won't function that way, it's going to be a lot cheaper for them to spend the time it takes to tune that system in to make it work that way than it's going to be for all the additional repairs they're going to have to do later because they're tearing things up. And this applies to IntelliPack RTUs, this applies to air handlers in a space, self-contained systems, you name it. Like, this is not centralized to just one type of system. This is across the board when we start talking a branch duct system. Pumps. Pumps are pretty straightforward. The big thing about pumps is, all the same principles apply. Where people get in trouble is controlling the building loop pressure and not running too much pressure. So had a scenario today. Chiller kept acting funny, kept tripping on some different alarms. Specifically, the one we've been dealing with was a low evap saturation alarm. And what it boiled down to was the loop had just enough pressure in it to confirm that it had water. So it didn't have any air per se, but it didn't have any stacked water in there. So we didn't have, we only had enough pressure at our low point to qualify for our head weight. So we had flow, but we were not, the equipment was not running very efficiently.
So it's acting like a starved evaporator, just wasn't able to.
Basically, it almost acted like it was having a load issue, even though there was plenty of load. Well, inevitably, we got that pressure up to about 24 psi on the return side. Everything just balanced right out. Beautiful. So the chiller started to tune in and balance. Actually, it was taking 2 chillers to try to keep up. We were able to actually reduce it down to just 1. That's all we needed. Just by getting that water volume in the pipe up to a proper point. You know, every stress on that pump is stress on that motor. But we can't talk about the motor without talking about what it's hooked to. So in the same way that the static pressure creates all this additional stress on a blower motor, even if it's belt driven, right? That same stress is applied at a pump level. So it's very critical we're paying attention to what our pressures are. And if we have water pressure gauges, it is important to have water pressure gauges on pump, right? If there's nowhere to put them, that's fine. You can't control that. But if they have the ability to have them, they should have them. Ohms and megging. This came up again in the last couple of weeks, and I want to bring it up as a discussion. What's the difference between continuity and ohms? So we'll use Fluke. I think they're one of the higher ones, for example. So Fluke, these aren't hard numbers, these are just estimated. Continuity is anything below 30. Man, my spelling today. Below 30 ohms.
Scribbler.
They make symbols for that.
Is
You don't get it.
tone, right? So if it's below 30 ohms, you're going to get a tone. Anything above, so 31 plus 31, want the symbol? How about that for a symbol? No tone. If you've got a motor that has 31 ohms to ground, is it still grounded?
Yes.
If you're testing that motor via continuity, are you going to know that it's grounded?
No.
You're not going to have a clue. In many meters, the continuity and the diode test overlap. That reading you get may be like a volt to DC reading. It won't actually even be your true ohms reading. So you won't even, in continuity mode, you won't even see what your actual ohms are. Some meters do, some don't. Many meters, which I think field piece, that cutoff is like 10 or 15 ohms. Anything more than that, it's not going to give you a tone. I think Fluke is actually somewhere between 30 and 50, actually, like legitimately. That's all it takes, that 1 ohm above. Does it change the outcome? No. You get the same exact result, you just don't know that you did. Now, one of the things we have to keep in mind too, so this is continuity test. This is why, before I get on the other thing, this is why I am so much against using continuity test for any kind of, unless you know that you're looking for a direct short, it's not the right mode or procedure to be using. Right, so there are applications where continuity is effective, okay? If you know that something is shorted and you're trying to find that short, it is a great method because you already know you've got a direct short to ground. But if you're going in and you're just doing general tests and you're analyzing a system and you're not actually, you don't know that there's a short, you just want to see what the readings are, continuity is not the direction to go. You have to go into ohms. And even when you go into ohms, you have to use the proper range. I've seen this before with technicians. They put their meter in manual ohms, and so usually most of your digital meters will have 3 ohm settings. It'll be M ohms for millions of ohms, K for thousands of ohms, and then just regular ohms, which the moment you get above the thousands, it's automatically going to show OL. Tell you how many times I've seen stuff misdiagnosed because they can't find a short. Everything says OL to ground. Well, in reality, they had their meter set to ohms, manual, and it couldn't auto range up to see the thousands of ohms that was actually there to ground. So it's very critical. It's okay if you want to do it that way. So I have a manual set meter, right? It's okay to start, you know, with that, but you have to start at the highest setting and work your way down. So in that particular case, I'm starting at millions of ohms, and if I see 0, I step down to 1,000. If I see 0 at 1,000 ohms, I step to just the hundreds of ohms to get the true reading. So 20 ohms is going to show 0 ohms at millions of ohms range and thousands of ohms range. But in hundreds of ohms range, it's going to show 20 ohms. So it's very critical that we're paying attention to that, and that we're reading what the indicator says, first of all. And two, we're using it properly. If you want to use manual range, fine, that's okay, but use it properly. That takes us into another part of that conversation is, what's the difference between a meter and a megger? It's all about the voltage. Any ideas what these voltages are on average?
Meter? It's like 5 volts or wherever the battery produces.
Yeah, anywhere from 0.5 to, I've seen up to 3 volts DC. Not that some may not go more than 3, but the majority of them, even Fluke, will cap out around 3 volts. A megger, on the other hand, usually will be anywhere from about 250 or 500 or 1,000 volts DC. So the vast majority of the time, I'm testing at 1,000 volts on commercial 3-phase equipment. Now, I've had the question asked to me before, well, it's a 460 volt motor, you're putting 1,000 volts on it, isn't that going to damage the motor? No. Because we're not trying to run the motor at 1,000 volts. This is 1,000 volts at like microamps. You're talking a very small amperage capacity, but a very large voltage charge. And the whole point of this test is to see if we're able to get any kind of electron flow through the winding. So you're not going to meg a motor winding to winding. You're megging a motor winding to ground. Which on a 3-phase motor, we haven't talked about that. I probably should have covered that in the beginning. A 3-phase motor, you're going to have the same ohm reading across all legs. If you've got one leg that's, you know, if you got a 2 ohms, and then 6 ohms, something's wrong. Something shorted, something screwed up, or these are shorted and why they're lower. Something broken here. Now on a single phase motor, your common to run may have, you know, 10 ohms. Common to start may have 80 ohms, and your run to start should have 90 ohms. This is a direct correlation to these, because literally this is reading through these. It's these two combined to get to this. Right. So if this is considerably different than the math you did in your head on this, something is wrong. Now the values change per the motor. These aren't hard set values.
But the math always has.
The math is the same. What you have to be careful of is multi-tap motors that have multiple speeds. And there's 2 ways that they do that. On a single phase motor, we'll draw it here. Your common, run, start, cap. There's a couple of ways that they do this. So in some cases, your lowest resistance is going to be your high speed. Automatically. Your lowest resistance is your high speed. Is going to generate the most amount of current. And the more current generated, the faster it turns. Or less flow. Let me rephrase that. Less about the current. The more flow allowed through the coils, the smaller the coil, the faster it allows it to turn on the rotor. By adding to that coil, allowing less flow because there's more resistance against it, it's going to turn slower. Between here and say we have a medium speed and a low speed. This could be a winding, or it could be a actual resistor, which is, so, and it really just depends on the motor manufacturer.
So as you increase that resistance on the speed taps, it decreases the motor speed. Right?
Yes.
Okay. Cool.
Yes. Which is exactly how a motor speed controller, it's a rheostat. Okay, you know what a rheostat is.
Is it a voltage? No.
Nope.
That's it.
The rheostat is a variable resistor. So variable
A varistor.
resistor. It's also called a see if I can spell it. Rheostat. And this will literally tie in through the common side. So you can take a single speed motor, and there's nothing fancy to this. It's literally just a box on the side of the, there you go, that's a box, isn't it? There's literally a box. It'll have a little turn dial.
You see these on exhaust fans a lot.
Yes.
Yeah, you see them on exhaust fans, you see them on fan power boxes.
I am.
Those are the two most common. You can put these on split system air handlers. And so you adjust this, and basically whenever you're adjusting the speed up, your ohms go down.
So what does that do to the time curve? Is it kind of
Doesn't do anything.
Okay.
You're literally, instead of having a motor that's got a built-in additional resistance to slow it down that we do through taps, we can get precise control with it through the motor speed controller is what it's called. The reality is it has a rheostat inside of it, is how it's able to do it, and you're just increasing or decreasing resistance through that rheostat to control how fast that motor turns. That's how you test these. So it'll have two wires coming off. You just take your ohms, read across it. You should see X number of ohms. You don't see nothing, motor won't turn on, probably your problem. That's part of what you can test is you may have a motor, and I've had this happen before, get customer out of a bind, that they were running on the, actually it was the heat. The heat was running on the low speed tap. Well, the point of the coil right here between the low and medium speed, actually no, it wasn't even that. It was between the medium and high, this exact scenario. It was a residential service call way back in the day. It's severed right here. The resistor, the winding, whatever was there broke right here. But the high was still connected. Well, that's all I had to do. I just moved the wires tap. Instead of being on low speed, I moved it over to high. It got them functional until we could get on the proper motor. Megger, so without getting too crazy into that, essentially my personal range, there's multiple lines of thought behind this. There's multiple processes. There's also using the voltage drop as well between what the output voltage of the Megger is versus how much is allowed to bleed to ground, right? So there's a couple of layers to this. The basic simple version that'll get you started is anything below 20 million ohms is considered bad. Okay? 20 to 40 million is caution. You're right on the edge. And then usually 40 plus, you're okay. Ideally, the ideal scenario is that your Megger will peg out OL every time to ground. By the time you hit 20 million and less, you may or may not get that motor to run on a starter. typically by the time you get below 30, hitting 20, and especially below 20 million, a VFD will likely not run. You might be able to put it in bypass, and it might run in bypass, but the VFD is going to trip on overcurrent or ground fault specifically. It'll probably trip on a ground fault, even though the starter, the bypass side of the drive will actually let it run. Because that drive, again, well, not up there anymore, the pulse width modulation has a very different characteristics than a pure sine wave. So that drive picks that leakage to ground up, and it ain't gonna play that game. And you can use these, nobody pays for it, but you can use these to do long-term failure prediction. Most of the time, electrical failure, right? Just like we use vibration analysis to predict mechanical failure on bearings, we can use mega ohms to predict electrical failure. Between the two, you could probably tell a customer years in advance a motor is going to fail before it ever does. Because what'll happen is, so my mega goes up to 2 trillion ohms. No, sorry, 2 billion ohms is what mine caps out at. Because of that, I'll start to see that, you know, between annual maintenances, that'll decrease. So say I walk in one year, it's got 1.5 billion ohms, okay? A year later, I've got 1 billion ohms. A year later, I've got 800,000 ohms. Same thing with the vibration readings. We come in, this inspection, we've got on our inner and outer bearing, 0.05 readings, okay? Extremely low, or 0.1. The next annual we did the next year, we're at 0.3. The next annual we did the next year, we're at 0.45. Trend here. If we were to take that much time, and it takes a lot of time to really analyze it and somebody paying attention to it, from a customer standpoint, theoretically, it's why we give them the reports, right? We're not technically paid to give them a full system analysis every time. We go in to do preventative maintenance to try to catch as much as we can that's in front of us. But if you wanted to start talking a real in-depth analysis, these are the readings you would be watching for every inspection. And you're looking for any deviation. And that deviation indicates to you, depending on the scale of it, all right, you've got about 6 months or you've got 5 years. Start budgeting now. Vibrations and alignments. One of the things, and instead of diving into the physical numbers of the readings and stuff, I don't think we need that as much as we do. We have to be careful with how we use those numbers, because many times I've seen a lot of stuff condemned and it not actually be a bearing issue, right? If your bearing readings, your inner and outer bearing are actually reading in okay range, but it's the horizontal, axial, and vertical that are the problems, don't write that motor up as bad bearings, because it's not. There's external conditions as to why those readings are that much. Even if you show bad, say they're only slightly bad bearing readings, so say they're a 0.6, 0.5 or 0.6, they're right there on the edge of condemnable on inner and outer. But yet your vertical, horizontal, and axial are all 2 and above, okay? Don't just immediately condemn those bearings. If they're not making noise, if you're not having other issues, but you can look at that motor and watch it sitting there doing this the whole freaking time, that's not necessarily a bearing problem. Just right there, it's very likely either an alignment, whether it be a pump or blower, or motor isolation, whether the mounting itself, what it's bolted to, and whatever springs, whatever it has. You know, those springs on those air handlers, they do break. You know, they will break and they'll get all lopsided, and that's part of many of our inspections. Technically, that is part of the scope. You're supposed to kind of look down in there and see what that spring looks like, see if it's sitting on its side. If we catch that, that's a motor killer. That spring, as insignificant as it may seem, that's a motor killer. And that applies to both scenarios, whether it's belt driven, direct drive, or pumps. It's got a coupling. That same principle applies to each of those scenarios. But if everything else checks out perfectly fine, you got horrible bearing readings, but there's no noise, there's no play, the motor's running fine, but all the readings are just crazy. Be cautious of the bearings and more of the alignment and mounting.